Hello, my name is Matthew Deptula, and today we're going to be taking a look at Chapter 6.2 of the Cosmic Perspective, Telescopes, Giant Eyes. Beginning with Part 1, the fundamental properties of a telescope. Let's take a look at two fundamental properties. First is the light collecting area, and this is how much light the telescope can gather at once. It's determined by the diameter of the telescope. When you square the diameter, you get the light collecting area. And what this also means is any kind of incremental increase in the diameter will lead to a much greater amount of light coming into the telescope. But secondly is angular resolution, and this is the smallest angle at which two objects can appear distinct. The human eye's angular resolution is about 1 arcminute. Let's dive deeper into it. This is an image of a man looking at a car as it passes by him. He's paying attention to the two headlights. When the car is far away, the two headlights appear as like sort of one blur. And that's because the angular separation of the two headlights is below something called the diffraction limit. But as the car gets closer, the two headlights become distinct. The formula for angular resolution is this, and it returns the angular resolution in arc seconds. Now, what is the diffraction limit? Well, it's the best possible resolution set by light interference. Larger telescopes will have a smaller diffraction limit, and longer wavelengths coming into the telescope will have a larger diffraction limit, and this impacts the resolution. Now, this is all caused by interference, and this occurs when any kind of ripples overlap. You'll have constructive interference where peaks add, and destructive interference when troughs cancel, and this applies, again, directly to light waves. And here's the formula for the diffraction limit. And again, this returns the diffraction limit in arc seconds. Moving on to part 2, here are the basic designs of a telescope. First is a refracting telescope, which uses a glass lens to collect and focus light. Here's what it looks like. The light comes into the top and it focuses through an eyepiece on the other side. An example of this was the largest refractor built in 1897, which has a 1 meter long lens. But the second kind of telescope is a reflecting telescope. And this uses a precisely curved primary mirror to collect light and reflect it into a secondary mirror that lies right in front of it. And there's 3 examples of what this looks like. First is the Cassegrain, where the light comes in through the top, bounces to the bottom, and comes into a secondary mirror bouncing to a focus point on the other side. And I would say this is the most similar to a refracting telescope. But the second kind is the Newtonian telescope, where the light reflects out to the side because it bounces off the bottom onto a mirror that reflects it out through the side of the telescope. And the third kind is sort of a variation on this, where it's on the other side. The light comes in, it bounces off a secondary mirror, and then a third mirror, which focuses out to the other side. And an example of a reflecting telescope is Gemini North in Hawaii, which uses the Cassegrain design with an 8 meter mirror. Now, some design limitations is because all research telescopes are reflectors. They require precisely shaped high quality lenses, made from high quality glass, and precise lens placement to ensure stability. An example of this is the Keck telescope, which uses 36 hexagonal mirrors to form one giant mirror. And here are some advancing mirror technologies for telescopes, and there are several that are being created. Now, the third part of this is the uses of telescopes. And the first use of a telescope is for imaging. Imaging instruments are effectively cameras, and they use filters to allow specific wavelengths of light through. And so in this instance, the Hubble Space Telescope is taking an image of NGC 3603, where it takes the blue, green, and red and combines it into one full color image. And this is another example where it's actually capturing invisible light. This is an X-ray telescope like Chandra, and it's taking an image of the N132D, and it's taking this invisible X-ray light. Now, another use of a telescope is spectroscopy, and this uses spectrographs which use diffraction gratings to separate light waves into different colors, and then this is recorded with a detector. Here's what it looks like. It's a very complex design, but effectively these are specialized mirrors that filter the wavelengths through, and then they are read on the other side. And this is what those readings actually look like, and they're determined by their spectral resolution. A lower spectral resolution will have blurry readings, while a higher spectral resolution will show the precise readings and the brightnesses of each wavelength. Now, the third use of a telescope is for time monitoring, which monitors the change in astronomical objects over time. An example of this is the change in light curves for the star Mira. As you can see, over a period of time, it gets darker and brighter. And so the sort of epiphany of all this is the Large Synoptic Survey Telescope, which has an incredible specs, like a 3.2 gigapixel camera, and over a 10-year period of time, it will produce 200 petabytes of data. And so the conclusion to all of this is that the role of an astronomer boils down to 3 things. They plan observations by determining what data to collect using telescopes. They analyze the data and then interpret it, and then develop models using that data. And what this all eventually culminates in is a global collaborative effort working to advance the human understanding of the universe. Thank you for watching.